Okay. As a reminder, in case any of you forgot, the first problem set was just due. You can still do it, but it's, I think, half credit at this point for a week. Hopefully you all did it. I'll put up the second problem set in the near future. So the topic that's going on right now is ramps, and sort of late in the last hour, we discovered that ramps really are in some ways best studied from the perspective of energy. So I brought up energy, and we'll see energy over and over again this semester. Ramps maybe not so much, but energy is so important and special in physics that I want to make sure that you all are comfortable with it. What makes energy important is that it is a conserved quantity in nature. If you've got questions about what that means, ask me. I'll just summarize it again. It's a quantity that has, for the case of energy, it has an amount, 10 Newton meters, which is synonymous. It means the same thing as 10 joules. It's a certain amount of energy. Energy, incidentally, has no direction. It's not a vector quantity, and we will see a couple of other conserved quantities soon that are vector quantities, that have a direction, namely momentum and its rotational equivalent, known as angular momentum. But anyway, conserved quantities are very rare in nature. There are only, there are half a dozen of them. The conserved quantities that we'll encounter this semester, there are 4 of them. Energy is one. The other 2 I just mentioned, momentum and angular momentum. And the 4th one is charge, electric charge, which we'll come to. But they're just super rare, and therefore something worth treating as something that's precious. And energy is something that an object has, or a system of objects have. And you can find that energy if you go looking for it. It can take 2 general types of form. There's energy in the motion of an object. So it's an object that is actively moving. The bowling ball, not now, but now, as it moves, it carries with it energy in its motion. The name for that energy, much of this you've heard before, it's called kinetic energy, the energy associated with motion. It doesn't care which way the object's moving, it cares how fast the object's going. And the details of how much energy it carries, I won't dwell on. The other type of energy that objects can have is energy stored in forces, what's known as ultimately as potential energy. You don't need any motion to have potential energies. The energy is in a wound or bent spring, or a stretched piece of elastic, or the force of gravity between this ball and the earth as I stretch them apart. So that energy stored in forces is in a potential form, often in an object that's not moving. Okay, so 2 forms for the energy, and the way in which you convey it from one object to the other, because it's conserved, you have to move it. And the way you move it is by doing work. And the act of doing work involves a couple of very specific things. To do work on this bowling ball, I have to push on it. I have to exert a force on it. No force, I'm not doing work. And it has to move. It's not about me, it's about it. It has to move a distance in the direction of my force. And so to the extent that, for example, I'm pushing up on it right now, I've talked about that before, to the extent it moves up, I do work on it. And the amount of work I do on it is the force I exert times the distance it travels in the direction of my force. So it's force times the distance. And the only part of the distance that matters is the distance in the direction of the force. So if I go up at an angle like this, my horizontal movement doesn't count because I'm pushing it up. To the extent that it moved horizontally, irrelevant. The extent it moved in the direction of my upward force, that counts. And you can calculate this. This is one of the few formulas, if you want to think of it as a formula, that I would like you to know, and you may see directly or indirectly in an exam. Suppose this weighs maybe 50 newtons. It's about right. Yeah, it's maybe, that may be way off. 50 newtons, and I move it up 1 meter, which is, about like that. I have done 50 Newton meters of work on it. I've given it 50 Newton meters of energy. It now has that energy stored in the force of gravity, so we call it gravitational potential energy. And I could take the energy out by doing the same amount of work, but with a negative sign. Negative amount of work, lowering it back down. So I took it back out. Okay? Well, got a couple questions last time that are worth talking about. The first is if I'm holding the ball still, so it's not moving anymore. Am I no longer doing work on it even though I'm holding it? And the answer is yes. Correct. I am not doing work on it right now. Zero work. I'm still exerting the force on it, but there's no movement. It's not moving in the distance in the direction of force. So why am I getting so tired? And so anyway, why am I getting so tired? It's because I'm not a very good statue. If I were a statue, I could hold the ball up like this. You can imagine a Greek statue of somebody with, I don't know, maybe they bowled back then. Holding it, has been holding it for 2,000 years, right? I'm simply imitating a statue. I'm not conveying any energy to the ball that wasn't there already. I'm getting tired not because I'm giving energy to the ball, but rather because I'm doing a lousy job of imitating a statue. To hold my muscles like this steadily, I have to consume energy. It doesn't vanish from the universe or even from me. It goes from chemical potential energy in me, energy stored in the forces within molecules and breakfast food. It's going from that form to thermal energy. It's going into a form of energy that a seemingly third form of energy. I told you about kinetic energy, potential energies, and then there's thermal energy. What's thermal energy? Actually, thermal energy is just sliced up pieces of the first two, kinetic and potential. Little bitty portions of kinetic energy, little bitty portions of potential energy, sprinkled around among all the molecules that are me. And so I am wasting nice energy, chemical potential energy, food energy, to make thermal energy. I'm getting hotter and hungrier. But it's all within me, just trying to pretend I'm a statue. Is that okay? So it happens all the time that you get in a situation where you're doing no work and yet you're getting hungry and hot. An example, another example of that would be lifting, what I was just doing basically, lifting barbells up and down. As you lift them up, you push up and they move up, and you put energy into them. That's real. You actually lost some energy. As you lower it back down, the energy comes back out and goes back into you. What form does it go into when it goes back into you? Well, it turns out we're not very good at receiving energy mechanically. So somebody gives us energy by pushing on us as we move in a distance in that direction of the force, and we change shape, we kind of can't do anything with that energy, so we turn it into thermal energy again. So this is why the lowering process can be just as much trouble to us, as challenging to us, as the raising process. Getting that energy back in and doing something with it that doesn't cause damage is tricky. Okay? Do I still have that question? I may have lost this question. I did lose a question. Okay. I had at one point a question up here about some of the machines over at the AFC, or just in general, the exercise machine, are more complicated than a dumbbell. For example, there are machines where you have to push them up as they go up, and then you have to pull them down as they come down. Any of you remember encountering machines like that? You do work both ways. You do work as you push up, and it moves up. It satisfies the requirements. You do work as you pull down, and it moves down. So that's a good thing. The energy is really continuously being taken out of you. You're not having to receive it back and to squander it as thermal energy. So it's in some ways it's a safer type of exercise. then putting the energy in, receiving it back. Here you put it in, you put it in, put it in, put it in. Another example of that, and since this is a class that I'm trying to give you things that are useful, regardless of what we cover, there are two sort of categories of stepmaster type exercises. Those if you've encountered machines where you're standing essentially on two pedals, and you push the pedal down, and then you lift it back up, and you're alternately doing this, and you're essentially not touching anything else. You're on those two pedals. And as you push the pedal down, and it moves down, the force you're exerting on it is approximately your full weight. How do I know that? Because you're not accelerating up or down, right? So you must have net force 0, approximately, on average at least. So it must be pushing up on you with a force equal to your weight. And you must be pushing back down on it with a force approximately equal to your weight. Everybody okay with this idea? So those pedals, you're pushing down on them with a force equal to your weight, and they're moving downward. You're doing work on them. And the work is related to your weight times how far they move. The more they move per second, the more work you're doing every second, which is measured, now it's energy per second that you're doing. And the name for energy per second is power. And power is measured in the metric unit of power is the joule, which is the metric unit of energy, per second. Joule per second. You also know that as the watt. So if you ever wonder what are watts, 100-watt light bulb and stuff like that, 100-watt, 1,000-watt heater, that's what it is. It's the amount of energy per second in the metric system. Okay, so you're there putting the energy in, and that is a machine that's always taking energy out of you. When your foot returns to come back up, to take the next step, the pedal barely pushes against you. It gives you a tiny bit of energy back because it's pushing up on you as your foot moves up, but not very hard. So there's a little bit of work back on you. The El Cheapo step machines, which you can purchase on late night TV, are just springs. You push it down, it do work on it. Yep, it gets the energy out of you. As you come back up, it pushes just as hard right back up, the whole way up. It gives you all your energy back. And you got to do something with it. And it's not nearly as comfortable as the machines that actually take the energy away and go do something else with it. All right? This is sort of food for thought next time you're hanging out at the gym. Another aspect of the Stairmaster, which is, my favorite aspect of the Stairmaster, so I can set you all up to become spies or something, is the amount of downward force you're exerting on those pedals matters. If you're pushing down with your full weight, every step that you make of this distance does your weight times this distance of work. But suppose you aren't pushing that hard. Suppose you're only pushing with half your weight. You're only doing half the work with every step. This is easier. Well, how would you push down with only half your weight? Hang on the bars. So those of you who have watched people doing the step machines and notice that they start after a while clinging to the bars to support themselves, they're reducing the work they're doing, and the work they're doing per second, which is to say the power that they're expending. It's just human nature. You start gravitating towards those bars to support yourself, and you kind of think, well, I'm still doing the same number of steps per second, but you're using less force to do it, and therefore doing less work. Is this okay? Or questions about it? Again, you can ask me live or by electronic. So anyway, the exercise machines are just filled with doing work and having negative work and so on. Let me point out that you can watch work conserve energy in an interesting way. Energy conservation shows up in the act of doing work directly. When I push the ball up and move it up, I do work on it. And the work is the upward force I exert on the ball times the distance the ball travels in the direction of the force. At the same time, watch what the ball is doing to me. The ball is pushing down on my hand with a force that's equal but opposite to my force up on it. So it's doing the exact opposite on me, pushing me downward as my hand moves upward. It's doing negative work on me, and the negative work that it does on me is exactly equal to the positive work I do on it. So I put, I don't know, 50 joules, like I think I said, into the ball. It does exactly the opposite and gives me negative 50 joules, sucks it out of me. And this is that's demonstrating that energy is a conserved quantity. The act of doing work, there are always two forces involved, always two things moving, and therefore always the energy moves, leaves one object and enters the other. You don't just make some up out of nowhere. It's like when you give somebody $50, their net worth goes up $50, yours inevitably goes down $50. It'd be nice if you just keep giving $50 bills away and nothing changes with you, but then money wouldn't be conserved. Same thing with energy. Okay? When someone pushes or pulls, are they doing different forms of work? The issue is always the direction of the force you exert times the distance the object you're pushing or pulling moves. So when I push up on the ball and it moves up, I'm doing positive work on it. On the other hand, if I am pulling up from below and it moves up, I'm also doing work on it. Doesn't matter whether it's a push or a pull. Figure out which direction it's in and figure out whether the object's moving in that direction. Then it's positive work. All right? So where all this figures into the ramp story is the key things that ramps do for us is allow us to lift things and therefore invest energy in them, but by using a different relationship between force and distance. So for example, if I want to lift this wagon straight up, of course it's not too bad right now, but as soon as I put blockhead here and there, it's now a lot harder. To lift this up, I have to use a big force. And if I want to get it a meter high, I have to use big force for 1 meter. What the ramp does for us, and so in doing that, I've done a certain amount of work on it. You know, its weight times 1 meter. Okay. If I go up the ramp, however, I can use a much smaller force to do the work. I push it up the ramp. As it moves up the ramp, I'm doing work on it again, but it's not going up very fast vertically. And so by the time I get 1 meter high and have given it the same amount of energy as I did by going straight up, I will have moved it along the ramp maybe 10 times as far. So if I go straight up with a big force over a little distance, I do a certain amount of work. In this case, I go at an angle over with a much smaller force for a much longer distance. And the product of the two, which is the work I do, stays the same. So if I go straight up and I do 50 joules of work, I just to pick a number out of the thin air. If I go along the ramp and I do, again, 50 joules of work to get it to the same altitude, and if I travel 10 times as far in doing it along the ramp, doing my work, I'll do it with 1/10 the force. All right? Well, just sort of see whether you have heard that. Let's try this one, so you can just now show it. So here you got a grocery cart, and it weighs 200 newtons, which what is 45 pounds I got. And you want to lift it up, just say that your car's at the top of some ramp or top of some rise. You're going to push the cart up the ramp at constant velocity, and it's going to travel 10 meters in order to go up vertically 1 meter. So it's 10 times the trip. Is that okay? The question is how hard and in what direction are you pushing as you take it up the ramp? Questions about the question? It's a lot of words, but it is what it, you know. Okay, go ahead and talk about it among yourselves. The majority have the right answer, but not everybody. I'll call it at the minute. 4, 3, 2, 1, 0. Wink. The answer is B. The force you need to exert on that grocery cart is only 1/10 the weight of the grocery cart. That's because you're going to use 10 times the distance to do the lifting that you would if you went, as you literally lifted it straight up. You're going to travel 10 times as far. So the work is spread out over 10 times the distance. If the distance is up by 10, the force involved is down by a factor of 10. And that's 200 newtons divided by 10 is 20 newtons. The force happens to be not straight up anymore, so E isn't it. The force that you exert is along the ramp because your job is to cancel the ramp force and push uphill just as with the same, just as strong as the ramp force pushes the cart downhill. So the point of that question is to show you that you can figure out how much force you're going to need to go up a ramp. It's just the weight of the object times a ratio. And the ratio is the ratio of how much you're going to lift it vertically divided by how far you're going to push it along the hypotenuse, the ramp's surface. So it's not rise over run. Run turns out to be this board. That's the movement horizontally. Alas, it's not rise divided by run. It's rise divided by distance along the ramp. That gives you the fraction of the force you'll have to use to get the cart up the ramp. And the university, like most places, has lots of access ramps constructed to allow people to lift themselves, people who can't simply walk upstairs or whatever, to lift themselves upward with gentler forces. Most people can't push up their weight or pull up their weight directly, too much. So you need to reduce the forces involved, and the shallower the ramp becomes, the smaller the forces you need to do the work of lifting along that ramp. And so somehow or other over the years, people figured out approximately the maximum steepness for an access ramp that's tolerable by most people. And I think there are sort of two limits. There's the limit where there's plenty of room to work with. You can, I think is it 12 to 1? You have to, the length has to be at least 12 times as long as the distance you rise up. And in a pinch, you can go down to 8 to 1 if there's really confined space. But basically, that's sort of the limit of what people can handle. So they're working with on the order of 1/8 their weight or 1/12 of their weight, trying to go up those ramps. Is that okay? I mean, you don't get something for nothing. You have to go 12 times as far or 8 times as far. How about this one? So you got that cart going up the ramp, and the ramp, it's the same ramp as before. It rises upward 1 meter for every 10 meters you go along the surface. Same ramp we had in the previous question. You let go of the cart, what happens? You okay with that? We'll finish up here. 5, 4, 3, 2, 1, 0. Yeah, it is downhill acceleration, and it's 1/10 the acceleration due to gravity in strength. The acceleration due to gravity, I'll remind you, is just under 10 meters per second squared, so this is about 1 meter per second squared. And it's consistent with what you've always seen, that if you let If I drop this, you know what's going to happen, right? It's going to accelerate the full acceleration of gravity. If I go down a ramp, this is sort of on the order of 10 to 1. It accelerates directly downhill because that's the direction of the net force on it. It's the ramp force. And it's weakened by the same factor, the rise divided by the distance. So it goes slower. All right? One last thing to point out with an object on a ramp is if I ask you what is an object on a ramp doing, and I don't give you much more information than that. For example, the cart is on the ramp and nothing else is pushing on it. What is it doing? Don't fall for an answer where I say it's, for example, going down the ramp or going up the ramp. Those answers are all velocity answers, and we don't know what its velocity is because we don't know its history. All we do know is that right now it's experiencing a downhill net force. And so what is it doing in response to a downhill net force? It's accelerating. Okay? It's accelerating downhill. So there are lots of cases where objects are on slopes, and we don't know whether they're going uphill, downhill, or an angle around all that, pinball going around a sloping surface. We don't know what its velocity is, but we do know it's accelerating right down the hill at a certain strength of acceleration that depends on the rise over the distance. Okay? With that, I think I'll leave. Can I draw a picture of this stuff? So here's the wagon on the ramp. I'll put wheels on it. This is the extent of my artistry. So in order to rise this distance, so you're lifting at that distance. Let's let that be 1 meter. 1 meter. To do that. If I go straight up with a ladder, and this thing, let this guy weigh 1 Newton. Give it a weight. It's little. It's a little apple. 1 Newton, 1 meter. To lift it straight up, I would use a 1 Newton force, and lift it 1 meter. I would do 1 Newton meter of work, which is the same as 1 joule of work. Incidentally, joule is spelled named after the physicist Joule, which is Joule, not like what Tiffany sells. So I would do 1 Newton meter the hard way, big force, little distance. On the other hand, if I can go along the ramp and travel 5 meters, I'm going to dilute the work by a factor of 5. And the force I use to push up that hill, 1/5 of a Newton now. Is that okay? All right. So that's enough of the ramp story, I think, unless you want to ask me more questions. But let me go on to another topic. And the topic to go on to, and energy will follow us now forever, is a seesaw. So why a seesaw next? It's because I've talked now the past number of days about things that go moving through the world in a type of motion that we can describe, or that is conventionally described as translation. And it sounds like foreign languages, but physicists talk about this as translational motion, where I go from one place to another. It's not the only kind of motion there is, or at least there are certain situations where translational motion language is not very helpful or tough. For example, if I'm doing this, well, yes, my hand is translating. It's going from there to there to there. But describing this with translational motion language like position and velocity stuff is just messy, and we can do better. And the seesaw is an example of another kind of motion because it doesn't go anywhere, right? It doesn't translate. It's kind of stapled in place. The motion that a seesaw undergoes is rotational motion. And I use the word rotational and angular kind of interchangeably. The official physical quantities describing rotation have the word angular in them by convention. It just is what it is. And I might sometimes call them rotational something, and I mean the same thing. So a seesaw rotates. And this is a topic that I have historically been able to spend way too much time on. And therefore, I'm going to try to keep it short and sweet. This is a physicist's version of a seesaw where the kids can not only go up and down, but they can go all the way around, which is probably a little more fun than their parents want them to have. So the point of this is that we can describe the seesaw's motion in terms of rotational physical quantities, so it's a good opportunity to talk about those quantities. We won't use them as much as maybe I would like over the next part of the semester, but you ought to at least know they're there. And again, they are not completely new and independent things of translational motion, but there are much better ways to describe the motion of a seesaw than to use the translational stuff. So what are the quantities that describe a seesaw's motion? Well, first off, we can consider at one moment in time, how is the seesaw, in effect, positioned rotationally? Remember, position is where I am. I'm here, I'm a certain distance from the reference point, in a certain direction, and so on. With something that rotates, there's the same kind of physical quantity around. An angular position, rotational position equivalently, who cares? So again, I need an origin. I need a reference point, and then I need an amount we're going to rotate away from that reference, and in which direction I rotate away from that reference. It's going to be very like position. And so here's the idea. Let's define the reference orientation as horizontal, and that I'm going to rotate it a certain angle around away from the reference, and I'm going to rotate it in a certain direction, like this way or this way. Those are different. Well, this guy's constrained in various ways. I can't really rotate it as freely as I would like, so I'm going to shift over to talking about myself. So I'm going to be the thing that shows you angular position. And I'll start by saying I need a reference point. The reference, which is really a reference orientation, so that if you want to call someone up on the telephone and tell them how I am oriented, what is my angular position, you would say, right now you'd say he's at the reference orientation. This is it. This is the standard we're going to start from. And now, the next thing you have to tell a person is, assuming that I'm not oriented like this, let me be like this, that I am rotated away from the reference by 45 degrees, which is a familiar unit of angle. As a note, there is a natural unit of angles. It is what it is. Mathematics gives us a natural unit of angles. Degrees are a convention. The natural unit of angles is a full rotation equals 2 pi radians. Radian is the natural unit of angle. And the word radian is often just left off from the script. I'm about to do a 2 pi rotation. There we go. Which is about 6.228. Okay? 6.28 radians. Radians are useful and important. I'm not going to worry much about them. I told you about them. You've heard them. We're done. Okay, so we're back. This would be 45 degrees in a more familiar unit of angle. Not enough information yet, right? Because there's a direction aspect of it. This is 45 degrees, and so is this, and so is this. Okay, they're all 45 degrees from the zero, from the starting point. So we need a direction. And by convention, the direction part of angular position, which it's a vector quantity again, I can't help it, that's what it is. It's got an amount and a direction. The direction part of the orientation is the rotisserie axis. So bind me up like a chicken on a rotisserie, or maybe it's a tofu turkey to be kinder to animals. Okay, so if I'm doing this, I'm rotating about the spit is a vertical line, right? I'm spinning about a vertical line. Hopefully you'll all visualize that. So this orientation, which we're trying to describe to somebody on the telephone, is a 45-degree rotation away from the starting point about a vertical axis. And now they know an awful lot about what I just did, how I'm oriented, but not quite enough. Hopefully you're okay with 45 degrees about a vertical axis that clearly distinguishes it from 45 degrees about a horizontal axis toward you guys. So this is 40. There's one ambiguity left in this, and it's an important ambiguity so it's an important ambiguity. This is 45 degrees about a vertical axis, but so is this. This is another, I rotated 45 degrees about a vertical axis like that. There are two choices. How do we decide which is which? Well, there's a convention that has shown up. It's an international convention, not the one you would attend though. The scientists, engineers, normal people finally decided to use this convention. And the convention it's known as the right-hand rule. You may have bumped into this before. And I will point out later that it's important to you, just independent of physics. The right-hand rule is this: to distinguish this orientation from this orientation, look at the rotation process, the way in which I was rotated about a vertical axis, and using your right hand, and it's got to be your right hand. If you're left-handed, sorry, you got to use your right hand. If you take your fingers and point the four fingers of your hand, or whatever number you got, rotate them, point them in the direction in which the rotation is arcing. So I'm going this way, right? Hopefully you can sort of feel that that's the direction I'm going. My thumb points in the official direction of that my angular position. Up. This is 45 degrees up. If I did the other one, that's 45 degrees down. All right? So use your right hand. Now, why would this ever show up in ordinary world outside of physics? Let me see if I can get this up here. Here. Look at this question. Most jars have right-handed threads. In fact, most things with threads on them, like bolts and nuts and screws and all that stuff, they're right-handed. There are exceptions, and they are really a shockaroo when you run into one. But if you're trying to take off the nuts and change your tire, and you have to remove the nuts and stuff on your car hub, it's going to be right-handed threads. Okay, so the jars follow right-hand thread, meaning the lid moves. That as you rotate it, the lid undergoes translational motion in the right-hand rule direction. And I meant to bring a jar in here and forgot, but it's okay. As you look down on the jar and you rotate it in the direction that opens it, or you're trying to open it, which way do you rotate the lid of the jar? Are you okay with the question of that? You're looking down on it. Basically, I'm asking you to notice that you've been using the right-hand rule your whole life to open jars. And if you're one of the people, and I'm now aware there are people who have to try both directions before you get the jar to open, now you can do it without having to try. You know exactly which way to rotate it. So which way do you want to rotate that lid as you look down on it to get the lid off? Any questions about the question? If it were Friday, this would probably be a bottle instead of a jar. Okay. 5, 4, 3, 2, 1, 0. Yeah, counterclockwise. And that is correct. And so some of you are still there trying to get at the bottle. I don't have anything I know I do. Most threaded things in our world are right-handed threads, which means that if you rotate them so that your fingers of your right hand are curling with the direction in which the surface is going, the object will move in the direction of your thumb. So this is the real story. The righty-tighty, lefty-loosey thing is kind of vague. It's kind of like, what's right? What's left? It's a little messy. This is the real rule, guaranteed to work on 99.5% of the nuts and bolts and screws in the world. Do I have a piece of wood to go to bore holes in? Here. So if you've got a normal screw, it's going to have a right-hand thread. If I rotate it this way, it's going to move in the direction of my thumb. So if I take it and go after this piece of wood and turn it with my right hand following my fingers, it will move into the wood. Of course, I can't get it started very well, but that's the idea. I can go into a knot and see. I still can't get it. Okay. So this will be true of simple screws. When you're trying to take off, you surely have or will encounter some nut or bolt or something that you want to remove, and you just can't get it started either direction. But you try it turning it one way, try turning it the other way. Nothing's working. And you think, well, maybe I'm turning it the wrong way. Which way do I need to turn it? It's the right-hand rule. With very few exceptions. One of the exceptions shows up on bicycle cranks. Some of the bicycle cranks have a left-handed thread on one of the pedals so that it doesn't come off while you're riding. It's done deliberately. It is a surprise the first time you try to take off the bicycle pedal and realize, oh, I can't. It doesn't follow the right-hand rule. It's the reverse. Okay, it's a left-handed thread. Any other questions about the right-handed rule stuff? So let me just finish off the physical quantities describing rotation. So angular position, this, as I've said, is 45 degrees up. 45 degrees down, this is 45 degrees towards you. All right. Like with translational motion, we've got a position. We also need a velocity. The rate at which angular position is changing with time is angular velocity. And it turns out to be a much more useful physical quantity for most people and physicists, engineers, than angular position. It shows up a lot in sort of normal stuff. So to have an angular velocity other than 0, I got to start spinning. So here we go. This is about 90 degrees per second, because I'm completing a revolution about every 4 seconds. So it's about 90 degrees per second. It's about a vertical axis. So far, so good. And following the right-hand rule, it's up. This is 90 degrees per second up. That's my angular velocity. Okay? I'll stop. Obviously, the reverse is 90 degrees per second down, things like that. I can't sustain 90 degrees like this very long. Not an acrobat. Okay? So when we start to describe how a seesaw moves, it's going to be doing first a few degrees per second. This is a few degrees per second away from you, according to the right-hand rule. Here's, that's away from you. And then they rocket the other way, a few degrees per second toward you, away from you, toward you. Well, for that to happen, for it to go from rotating one way to rotating the other way, its angular velocity has changed with time. There's a rotational angular version of acceleration too. So this is angular acceleration when it goes from going one way to going the other way, rotationally, right? And there is an influence that causes angular acceleration. It doesn't happen for nothing. If I get this guy going and no influence that affects rotation shows up, it coasts. It coasts rotationally. It's got inertia rotationally. And it does. Just as we had inertia, an object at rest stays at rest, an object in motion continues in motion. That was in the world of translation, going somewhere. This is, and it's not perfect because there's some friction around, but this is inertia, an object that's rotating. If it's at rest, it stays at rest. If it's rotating, it continues to rotate about a fixed axis in space at a steady speed. It rotates at constant velocity, angular velocity in this case. Okay, so objects don't change their angular velocity for nothing. That angular velocity is changed by an influence, like a push or a pull, but it's not a push or pull for rotation. It's called a torque, T-O-R-Q-U-E. So to make something undergo angular acceleration, you have to twist it with a torque. Another torque. Okay? So we have the three motional physical quantities: angular position, angular velocity, which is how angular position is changing with time, and angular acceleration, which is how angular velocity is changing with time. All right? The cause of angular acceleration is a torque, and there is a resistance to angular acceleration, a measure of the rotational inertia. And I call that measure of rotational inertia rotational mass. Just like mass, mass fights acceleration. Rotational mass fights angular acceleration. The official name for what I'm calling rotational mass it's called moment of inertia. And it's got some complications and messiness, and it's also a wordy name. So for the most part, we'll just call it rotational mass. But some objects are easier to undergo angular acceleration than others. It's easy to spin a little ball. It's much harder to spin a bowling ball. It's also much harder to do something like this, where there's not a lot of mass here, grand total, but a lot of the mass is very far from my hand. So it turns out that mass and rotational mass are interrelated. And an object that has a lot of mass far from the place you're rotating it about has a big rotational mass. This is hard to rotate back and forth. Rotationally shaking it is tough. This has the same mass as, I don't know, this guy. In fact, this has more mass. And it's easy to rotationally shake it because all the mass is in my hand. Okay? Here it's far apart. And to finish up for the day and set the stage a little bit for next time, I'll ask you one last question, just what you wanted as you're packing up. Get this out of here. Not that one. There it is. Okay. You and a child half your height lean out over the edge of a pool at the same angle. So you're holding onto a railing or something. You're both leaning over the pool, and you let go at the same moment, and you tip over. Who hits the water first? You okay with the question? See what you think. We'll go to 30 seconds, and then I'll show you the answer. 3, 2, 1, 0. T-ding, T-dee. The majority are going for the small child. So place your bets. And here we go. So here's the small child. Here's you. You're going to pivot about your feet, because that's ready, get set. Small child hit first. And just to give you, so it's not a magic show, why did that happen? It's because as these guys are leaning, they're experiencing torques due to the Earth's gravity. The total story behind the torques is for our future. It's a little tough to, they are being twisted by gravity. So the cause is the torque. The resistance is the rotational mass. And if you don't believe it, try it yourself. The rotational mass of you, tall person, is huge because so much of the mass is so far from the pivot. That makes this thing very hard to rotationally shake. This is easy, okay? this has 8 times the rotational mass of this guy. And that slows down the angular acceleration terribly. So when the dust settles, the little guy falls faster, rotates faster. It just undergoes much bigger angular acceleration and hits first. So we'll get the rest of the story behind that on Friday.